elementary course in synthetic projective geometry by Derrick Norman Lehmer. Chapter 1 continued, One-to-One Correspondence. Section 7, Axial Pencil, Fundamental Forms. Section 8, Perspective Position. Section 9, Projective Relation. Section 10, Infinity to One Correspondence. Section 11, Infinitudes of Different Orders. Section 12, Points in a Plane. Section 13, Lines through a Point. Section 14, Planes through a Point. Section 15, Lines in a Plane. Section 7, Axial Pencil, Fundamental Forms. A similar correspondence may be set up between the points on a line and the planes through another line which does not meet the first. Such a system of planes is called an axial pencil, and the three assemblages, the point row, the pencil of rays, and the axial pencil, are called fundamental forms. The fact that they may all be set into one-to-one correspondence with each other is expressed by saying that they are of the same order. It is usual also to speak of them as the first order. We shall see presently that there are other assemblages which cannot be put into this sort of one-to-one correspondence with the points on a line, and that they will very reasonably be said to be of a higher order. Section 8. Perspective Position. We have said that a point row and a pencil of rays are in perspective position if each ray of the pencil goes through the point of the point row which corresponds to it. Two pencils of rays are also said to be in perspective position if corresponding rays meet on a straight line, which is called the axis of perspectivity. Also, two point rows are said to be in perspective position if corresponding points lie on straight lines through a point which is called the center of perspectivity. A point row and an axial pencil are in perspective position if each plane of the pencil goes through the point on the point row which corresponds to it, and an axial pencil and a pencil of rays are in perspective position if each ray lies in the plane which corresponds to it. And finally, two axial pencils are perspectively related if corresponding planes meet in a plane. Section 9. Projective Relation. It is easy to imagine a more general correspondence between the points of two point rows than the one just described. If we take two perspective pencils, A and B, then a point row A, perspective to A, will be in one-to-one correspondence with a point row B, perspective to B, but corresponding points will not, in general, lie on lines which all pass through a point. Two such point rows are said to be projectively related or simply projected to each other. Similarly, two pencils of rays or planes are projectively related to each other if they are perspective to two perspective point rows. This idea will be generalized later on. It is important to note that between the elements of two projective fundamental forms there is a one-to-one correspondence, and also that this correspondence is in general continuous. That is, by taking two elements of one form sufficiently close to each other, the two corresponding elements in the other form may be made to approach each other arbitrarily close. In the case of point rows, this continuity is subject to exception in the neighborhood of the point at infinity. Section 10. Infinity to One Correspondence. It might be inferred that any infinite assemblage could be put into one-to-one correspondence with any other. Such is not the case, however, if the correspondence is to be continuous between the points on a line and the points on a plane. Consider two lines which lie in different planes and take m points on one and n points on the other. The number of lines joining the m points of one to the n points of the other is clearly mn. If we symbolize the totality of points on a line by infinity, then a reasonable symbol for the totality of lines drawn to cut two lines would be infinity squared. Clearly, for every point on one line, there are infinite lines cutting across the other, so that the correspondence might be called infinity to one. Thus, the assemblage of lines cutting across two lines is of higher order than the assemblages of points on a line. And as we have called the point rows an assemblage of the first order, the system of lines cutting across two lines ought to be called of the second order. Section 11. Infinitudes of different orders. Now it is easy to set up a one-to-one correspondence between the points in a plane and the system of lines cutting across two lines which lie in different planes. In fact, each line of the system of lines meets the planes in one point, and each point of the plane determines one and only one line cutting across the two given lines, namely the line of intersection of the two planes determined by the given point with each of the given lines. The assemblage of points in the plane is thus of the same order as that of the lines cutting across two lines which lie in different planes, and ought, therefore, to be spoken of as of the second order. We express all these results as follows. Section 12. If the infinitude of points on a line is taken as the infinitude of the first order, then the infinitude of lines in a pencil of rays and the infinitude of planes on an axial pencil are also of the first order, while the infinitude of lines cutting across two skew lines as well as the infinitude of points in a plane are of the second order. Section 13. If we join each of the points of a plane to a point not in that plane, we set up a one-to-one correspondence between the points in a plane and the lines through a point in space. Thus, the infinitude of lines through a point in space is of the second order. Section 14. If to each line through a point in space we make correspond that plane at right angles to it and passing through the same point, we see that the infinitude of planes through a point in space is of the second order. Section 15. If to each plane through a point in space we make correspond the line in which it intersects a given plane, we see that the infinitude of lines in a plane is of the second order. This may also be seen by setting up a one-to-one correspondence between the points on a plane and the lines of that plane. Thus, take a point S not in the plane. Join any point M of the plane to S. Through S, draw a plane at right angles to MS. This meets the given plane in a line M, which may be taken as corresponding to the point M. Another very important method of setting up one-to-one correspondence between lines and points in a plane will be given later, and many weighty consequences will be derived from it. An elementary course in synthetic projective geometry. This book was written by Derrick Norman Lehmer, Assistant Professor of Mathematics, University of California. It was published by Ginn & Company, Boston, 1917, and is now in the public domain. The text is available for free download at Project Gutenberg, read by Jim Renholt. Programming and illustrations by Jim Renholt, 2020. Corrections and comments are appreciated. Thank you for listening.